All right, so today we're going to continue talking about the correlation coefficient. Like we talked about in lesson 7, if you have not watched the lesson 7 video, you need to go back because in that video, I talk about what the correlation coefficient is and what it means, and we're just going to continue practicing that in this lesson. So once again, the correlation coefficient is just that R value. That's going to describe the strength of your line of best fit. Okay. So in this first activity, it says match the variables to the scatter plot you think they fit best. Be prepared to explain your answers. Okay. So we have 4 different X and Y variables here. So these 2 are going to go together. These 2, that, and that. Okay. Those are all going together. Okay. So what I need you to do is I need you to read through those, and then based on what they are, we're going to determine if there's any sort of association between those 2 things. And if there is or there is not, we're going to try to imagine what that data would look like and match it to one of these 4 scatter plots. So obviously there's 4 situations. You only see 2 graphs on your paper, but if you turn the page or look over at the next page, then you'll see the other 2 graphs. Okay, so just some observations I'm going to make. This first one, both my X and Y values are increasing and all of my data is very condensed and close together. Okay, this one, you can tell it's increasing. It's a little bit more spread out. This one doesn't look like it has any sort of connection. It's kind of all over the place. And this one, as my X values are increasing, my Y values are decreasing. So I'm going to do the first one with you. Okay, it says the daily low temperature in Celsius for Denver, Colorado. Okay, so that's my X value. All right, and then the boxes of cereal in stock at a grocery store in Miami. All right, so what do you think the association is between the temperature in Colorado and how much cereal is in stock in Florida? Okay, just off the top of your head, do those things to even seem like they go together? No, probably not. So we can rule out this one because those have a really strong correlation. These even more strong than what you'd think. In my opinion, the temperature and the amount of cereal that's in stock have nothing in common. Therefore, their data is going to show that as well. So I would think that this first one is C because that data is so sporadic and there's no correlation here. So that's going to match that description. All right, so the next one, it says the average number of free throws shot in a season. Okay, so free throws shot in a season, not necessarily made, just attempted. Okay, the average. And then the basketball team score per game. Okay, so we know what we know about basketball is that free throws happen a lot in every basketball game. Okay, so this is the average in an entire season, not necessarily per game. Okay, and then the team score per game. Okay, so and what I think is that yes, there is going to be a connection between free throws shot in a season. There will be some connection, but not necessarily to each individual game score. Okay, now if it was the free throws shot and scored per game, I think, and then the score, I think that would be a very strong correlation that we could tell. I think there's going to be some correlation. I don't think it's going to be super strong, but I do think if these are increasing, then this one's also going to be increasing. So if I had to choose one, I would think it would be B. Okay, so we've got C and B. That leaves A and D. I want you to look over these. I'm going to give y'all about a minute and a half. I want you to attempt those on your own. Read through those. We've got the student's height in feet. So is the student's height in feet and the student's height in inches. Okay, is there a direct correlation between feet and inches if both of them are talking about the height? Okay, so look at A and D and see if you can decide which one matches that. All right, then we have 4. It says the number of minutes spent in a waiting room. Okay, so imagine yourself in a doctor's office. You're waiting there. And so think about if you wait for a really short amount of time. Think of how satisfied you are with your visit. Okay, probably going to be a lot happier. So your satisfaction rating is going to be high. So a shorter amount of time equals a high satisfaction rate. Okay, so when the X value is low, your Y value is high. Okay, so what about the longer you wait? So that X value is getting longer and longer. What's going to happen to your satisfaction rating? It's going to start going down. Okay, so that's going to have a negative correlation. So what's the only one with a negative correlation here? D. Okay, so if that one's D, then that would only leave that one as A. Okay, so you can see there's a correlation between how close together the data is and what you're actually talking about. Obviously, if your X and Y variables have nothing to do with each other, then your data is going to be really spread out and not have no correlation. But if they directly go with each other, like your height in feet and your height in inches, those are going to be exactly correlated into a really straight line. All right, moving on to this next problem. You will need Desmos for it. Don't roll your eyes. I know you hate it, but it makes our lives easier. So here we go. It says Priya takes note of the distance the car drives and the time it takes to get to the destination for many trips. Okay, so our X value is our distance, and then our Y value is our time. Okay, so we've got all of this data in it. It says distance is one factor that influences travel time of Priya's car trip. What are some other factors? Okay, so I want you to imagine you're driving from West Side and you're driving across town and you're driving in like school traffic. All right, so what are some things that can affect? We already know the distance. We're driving across town. That's going to affect how long it takes us because it's going to take us a specific amount of time to get there, right? Okay, but what are some other things that could influence it? Maybe stops that we have to make along the way. Okay, what if we have to get gas? The car breaks down. We could get pulled over. There could be construction. Okay, so it's not every time if we left school at the same time every day and we went home, the time it takes us to get from school to home may not always be the exact same amount of time because we know all of these things can change. Okay, so the data is always going to be a little bit scattered. Okay, so it says which of these factors, including distance, most likely has the most consistent influence on all car trips? Explain your reasoning. We're moving on. Number 3, use technology. What are we going to use? Desmos. Please get this practice in. A lot of y'all are still confused on some of the steps, and I'm literally working through the problems here. So it's best to do it with me. We're going to create a scatter plot of the data and add the best fit line to the graph. Okay, I'm going to pause my video for just a second just to type in my data to Desmos so that you don't have to watch me do it, but you also need to be doing that as well. All right, so as you can see, I have my Desmos pulled up over here. I've taken my time and made my table and added in all of my data to it. If I were to zoom out, you can see all my data is kind of scattered all about the place because the further we travel, the longer it's going to take. So we have that, it's increasing, it's positive. Okay, so now we are going to create the line of best fit, which is what our question asks us to do in our book. So I'm trying to have that. Okay, right here. Add the best fit line to the graph. Okay, here we go. So you click down here. Okay, here's the little formula, Y1, because we're pulling from this Y1 table up here. Squiggle line, MX1 plus B. Okay, so we see that that line goes directly through the middle of all of our data. And then if we scroll down here, we get the slope and the y-intercept, okay? So we are going to write that information down over here. So we want it in y equals mx plus b format, okay? Because that is the equation for a line, okay? That's what we talked about in the last unit. So we have y equals, our m is right here, 0.92, okay? Most of the time your book has you round it to the second decimal, so it's 0.92, and that 8 rounds it up to a 3. So it's 0.93 is my m, or my slope. Got to add my x, plus we've got our b down here. We got 4.14, and that 6 will round it up to a 5. So my b value, b, will be 4.15. Sorry, I'm out of my blank. All right, so that is our equation for the line of best fit, aka it's the equation of this line right here that we just created. All right, and it says, what do the slope and y-intercept for the line of best fit mean in this situation? Okay, we have a lot of trouble with these from what I'm seeing on the homework, and a lot of people are just typing nonsense into it. So really listen to me here. Let's start with the slope. Okay, so my slope is 0.93 here. Okay, so that's the change of y over the change of x. Okay, so what is our y value talking about? It's talking about the time. Start typing. Okay. The time is, okay, my slope is positive 0.93, so the time is increasing by 0.93. What are we measuring in? 0.93 minutes. For every one, now we look at the x value. What are we talking about? The x, the distance, for every 1 mile. Okay, so for every 1 mile we travel, it's taking us about 0.93 hundredths of a minute. Okay, so almost a minute to travel 1 mile in our car. Okay, and also how fast we get there also depends on how quickly we are driving. So that the factor that's most likely to influence it is going to be the speed we're traveling. Okay, and that's really evident here when we talk about the slope. Okay, so next question, what does the y-intercept mean? Okay, so the y-intercept is 4.15. Okay, and actually I'm going to write it like this. 4.15. And the reason I wrote it like this is because the y-intercept is literally the point that is crossing through my y-axis right here. So right there it is. I just rounded mine. Okay. So it's a coordinate that we're talking about. So this is my x value and this is my y value. So you literally just have to describe what that x and y value is in the situation. X is the distance. So we can literally say, oh my gosh. Let's do this. Let's bring it back. When the distance is 0, because that's what our x value is, the distance is 0, our time is the time it's going to take us to get wherever we're going is already at 4.15 minutes. All All right, so I want you to think of how we haven't traveled anywhere, but it's already taken us about 4 minutes, a little over 4 minutes to go. How does that make sense? Think of when you're getting in the car. What are some things that slow you down in the mornings? Oh, you forgot something. You didn't get the keys. The windows have to defrost. You're trying to find a good song. You know, whatever happened, all those things affect how much time it takes to actually start traveling. Okay. Your car is still parked in the driveway at this point, but it's going to take you about 4 minutes to take off. Okay. In this particular situation, that's not in every situation, but that is what it means. When you're explaining your y-intercept, you just, this is your x. Your x is always going to be 0 in the y-intercept. And then this is always going to be talking about whatever that y value is. Okay. Moving on to the next question. And I know there was some like that in your homework. Okay. Okay. Sorry if my screen looks a little different. I'm having some technical difficulties over here. All right, number 5, once again, it wants us to use technology to find the correlation coefficient. Okay, we have not talked about how to use technology to find the correlation coefficient. Based on the value, how would you describe the strength? Okay, so once again, that correlation is the R value. Okay, once again, Desnos is going to make your life so much easier. So just going right back to where we had, that graph earlier and we typed in that line of best fit, it gives us our correlation coefficient right here, the R value. It's 0.989. If we rounded that up, it would be 0.99. Okay, so my R value is 0.99. So we learned in lesson 7 that the closer this number is to +1 or -1, the stronger the correlation of your line of best fit and its data. So based on the fact that it's 0.99, how would you describe the strength of it? I would say it's strong as opposed to being weak. Okay. Also, I noticed that it's a positive 0.91. Okay. And the reason we talked about it's being positive, it's that positive or negative is just describing the slope. Okay. So if we go back to that, we can see it's increasing. It has a positive slope. So it's a strong positive correlation. Okay. So write down strong and positive. All right. Number 6, it says, how long do you think it would take Priya to make a trip of 90 miles if the linear relationship continues? So once again, this is how do you think, AKA, what do you predict? What do you estimate? Okay. So since we are estimating, we have to use our line of best fit. So I'm just going to rewrite my equation. Y equals 0.93x plus 4.15 that we came up with up here. All right. And it says Priya is going to make a trip of 90 miles. Okay. So where in our table does it talk about miles? Is that our X or our Y value? Let's go check. Miles, that's our X value. Okay. So they told us that X equals 90. Okay. And it wants us to see how long that would take. So we're trying to find the Y because Y is talking about time, how long it would take. Okay, so we have a equation. We have a variable. What do? We plug it in. Okay, so what you're going to do is you're going to write Y equals 0.93, but instead of X, we're going to plug in that 90. And we're going to do plus 4.15. And then we are going to simplify it. So I have Y equals, I don't have my fancy calculator with me, so I'm going to use my phone. So we have 0.93 times 90, which gives us 80. 3.7 plus 4.15. Okay, so I'm going to add on that 4.15, and my final y value is 87.85. Okay, so this is my estimate. Don't forget, it's going to take about 87.85 minutes to travel 90 miles. It says, if she drives 90 miles, do you think the prediction you made will be close to the actual value? Well, because we had a very strong positive correlation coefficient, yeah, I do think this is going to be very close to the actual value, because based on the rest of my data, it's very close to the line of best fit. Okay, so because I have a strong correlation coefficient, I can be confident in this estimate. Moving on, this part will be really easy, I think, for y'all. So don't panic because there's 6 questions to it. Okay, these aren't like it's not like 8.2. It says, for each situation, describe the relationship between the variables based on the correlation coefficient. Make sure to mention whether there is a strong relationship or not, as well as whether it is. Make sure you tell whether it's a strong relationship or not as well, aka you can just put it whether it's weak, and if it's a positive or a negative. Okay, so this first one we have is the number of steps taken per day, that's X, and the number of kilometers walked per day. Oh my gosh, it's late. I'm saying all the words wrong. Okay, so just thinking about that, yeah, I think if I take a lot of steps in a day, I'm gonna travel a larger number of kilometers. Okay, well, no need to think too hard because they give us our R value. Okay, first thing I notice is that it's a positive number, so I can go ahead and write it. Okay, it's also really close to +1. Okay, so is that a strong relationship or a weak one? It's strong. Done. So I have a strong positive relationship. Okay, I think you'll get 2 easily, 3 easily. I'm going to help you with number 4. The rest I think you should get pretty easily. This is where people get confused. They're like, okay, what's considered strong and what's considered weak? Okay, where's like the cutoff point? Okay, so then you're going to get to one like this. Okay, so we have the amount of fat intake per citizen of a country and the average cancer rate of a country. So they're trying to see here is if there's a correlation between how much fat you eat in your diet, like fatty foods, and whether that causes cancer. Okay, and right here we've got 0.73, which isn't super close to 1, but it's not really close to 0 either. It's honestly closer to 1, but you wouldn't actually consider this strong. Once it drops below about like 8, like in the 80s, really, once it drops below that and it kind of lands into like the 50s, so like high 50s, 60s, and 70s, those are considered moderate. Okay, so just like halfway in the middle. It's not super strong. It's not, you wouldn't say it's weak either. We don't want to say, oh yes, if you eat a lot of fatty foods, that causes cancer. Okay, so you can see how that could be risky if you say that has a strong correlation. Okay, so that one would just be moderate. It's also positive, so it's a moderate positive relationship. All right, I'm going to give you a couple minutes to do those other 4. That shouldn't take you long at all. And then we will talk about it. I'm going to give you about a minute and a half, and then we can discuss it together. Please don't fast forward me. Please just do your work and try to understand what we're doing. About 15 more seconds. All right, here we go. It says our X value is the temperature of a rubber band and the distance the rubber band can stretch. Okay, so this has a R value of 0.84. Now, while that's not super close to 1, this would be still considered a strong positive correlation between the hot, I guess, as the temperature increases, the distance of the rubber band would also increase according to this data. Next, we have the car weight and the distance traveled using a full tank of gas. Okay, so does the weight of the car affect the distance traveled using a full tank of gas? Well, think about how cars work. If their cars are heavier, okay, then the further that you travel is also increasing. Okay, the slope is going to be negative, okay, because you're traveling more miles, but the distance for a full tank of gas is decreasing. Okay, so this is a strong negative relationship. Okay, because the R value is negative and it's still close to 1, so it's still strong. It's just has a negative slope. All right, next we have the score on a science exam and the number of words written on an essay question. Okay, so will your science grade be affected by how many words that you put in the essay question? No, it will not. You can put a lot of nonsense word into an essay and not score very well on it, okay? So those are not directly correlated. So this one have a weak positive relationship, okay? You can't write more or less words and score better or worse. Those are not directly related. We know it's all about whatever the answer is. And finally, we have the average time spent listening to music per day and the average time spent watching TV per day. Okay, so is there a correlation between listening to music and watching TV? No. We have a weak negative relationship. Okay, so this graph would be decreasing, but like very spread out and scattered. You would not be able to really see any sort of relationship or correlation between those two variables. All right, there's an are you ready for more? We are not doing that. All right, so it says the value, I don't know what page it's on, the value for the correlation coefficient can be used to determine the strength of the relationship between two variables represented in the data. It says in general, when the variables increase together, we can say they have a positive relationship, just like a positive slope. If an increase in one variable tends to be paired with a decrease in the other variable, it's negative, aka if you looked at a graph, it would be decreasing. When the data is tightly clustered around the best fit line, we say it has a strong relationship. And when the data is loosely spread around the best fit line, we say there is a weak relationship. Okay, here's this just review from lesson 7. A correlation coefficient with a value near 1 or -1 suggests a strong positive relationship between the variables. This means that most of the data tends to be tightly clustered around a line, and when one of the variables increases in value, the other does as well. The number of schools in a community and the population of the community is an example of variables that have a strong positive correlation. Obviously, if you have a lot of schools in the community, that they're probably there because of the amount of people in that community. Says when there's a large population, there's usually a large number of schools. Small communities tend to have a fewer number of schools. Yep, that makes sense. Next, it says similarly, a correlation coefficient near -1 suggests a strong negative relationship between the variables. Again, most of the data tends to be tightly clustered around a line, but now when one variable increases, the other decreases. The time since you left the house and the distance left to reach the school has a strong negative correlation. Obviously, the closer you get to school, the farther you're getting away from home, okay? So that is going to be decreasing. Weaker correlations mean there may be other reasons the data is variable other than the connections between the two variables. For example, the number of pets and the number of siblings has a weak correlation. There may be some relationship, but there are many other factors that account for the variability in how many pets you have and how many siblings you have, okay? Just because I have one brother doesn't mean I can only have, 2 pets, okay? There's no correlation there. Says, how much more we got? That's the last part. All right, it says the context of the situation should be considered when determining whether the correlation value is strong or weak. In physics, measuring with precise instruments, a correlation coefficient of 0.8 may not be considered strong. In social sciences, collecting data through surveys, a correlation coefficient of 8 may be very strong. Okay, so basically what that's saying is depending on the specific situation you're in, it's going to determine what is considered a strong or weak relationship. Okay, so it's really depending on what you want. You want a really close correlation coefficient if you're doing something like physics and medicine and stuff like that, because you want it to be really dang accurate, okay? But now if you're doing something just for like survey purposes and like summaries and research and stuff like that, it doesn't have to be as precise. So that value could be very strong. All right, that's all for lesson 8. If you have any questions, please let me know, and please be keeping up with the videos.